This is the review for our test on inequalities and linear equations, starting with page 1. Problem 1 is an SAT test prep question. It's one of these quantitative reasoning or quantitative comparison questions. We're comparing the value of x, the quantity x, to 9/2. But before we can get a sense of the value of the quantity x, we need to look at these two inequalities. We know that 2x minus 1 is greater than 5 and 2x minus 1 is less than 9. That could have been written differently. I'll show you what I mean. That could have been written as 2x minus 1 is greater than 5 and less than 9. That's how a compound inequality like this is typically written, but I broke it up this way because this is the way we were looking at compound inequalities with the words and or, and means the intersection. So the values of x have to satisfy both of these inequalities. And so in order to try to get a sense for the values of x, the possible values of x, we need to solve both of these inequalities first and find out what x is greater than or what x is less than. So we'll do that first. And anytime we're solving an inequality, we solve it just like an equation. The only thing we need to look out for is if we multiply or divide both sides by negative, then we need to reverse the inequality because we're taking the opposite of both sides at that point. Okay, so here I want to isolate the variable x, so I'm going to add 1 to both sides of the inequality. And negative 1 plus 1 is 0, so I'm left with 2x is greater than 5 and 1, 6. Then I need to divide both sides by 2, and we get x is greater than 3. If x is greater than 3, it might be still could be less than 9/2, or it could be more than 9/2, or it could be equal to 9/2 because 9/2 is greater than 3. Let's see what happens when we do this side. Again, I'm going to add 1 to both sides of the inequality. And I get 2x is less than 10. Then divide both sides by 2. I get x is less than 5. At no time in either of these solutions did I multiply or divide both sides by a negative, so there was never a need to reverse the inequality. So x is greater than 3 and x is less than 5. So what could x be? X could be 3.1. That would satisfy both of these inequalities. That would still be greater than 3 and less than 5. Or x could be 4.9. That would also be greater than 3 and less than 5. 9/2 is 4.5 or 4.5. So it's possible for x to be, for this quantity A to be, the quantity in box A to be less than the quantity in box B. It's possible for the quantity in box A to be greater than the quantity in box B, and really it could also be equal to the quantity in box B. So there's not enough information to tell which is greater in this case. Problem 2, we need to create two sequences below, one arithmetic and one geometric. Begin by first choosing a common difference and a common ratio for each sequence. So we remember that arithmetic sequences increase or decrease by some common amount, and so that's called a common difference. And so if I choose a common difference, for example 2, then I can just write my sequence starting with any number. I'll just start with negative 3. If I'm increasing by 2 each time, that'll be negative 1 would be the next term, 1 would be the next term, then 3, then 5, then 7, ... This arithmetic sequence has a common difference of 2. If I take a term and subtract the previous term, I get a difference of 2 each time. For a geometric sequence, there's a common ratio, not a common difference. And so I'll use a common ratio of 3 here. And I'm going to start with something like 1/9. If I multiply 1/9 by 3, I get 3/9, which is 1/3. If I multiply 1/3 by 3, I get 3/3, which is 1. If I multiply 1 by 3, I get 3. 3 multiplied by 3 is 9. 9 multiplied by 3 is 27. So this is an example of a geometric sequence with a common ratio of 3. Problem 3 asks us to graph the two linear equations below. They've been nicely given to us in slope-intercept form. This form y is equal to mx plus b, where y is isolated on one side of the equation. And on the other side of the equation we have our variable term with x multiplied by some coefficient, which is the slope of the line. And to that variable term we're adding some constant term, and that's the y-intercept. So we know m is slope, and b equals the y-intercept. So if we simply identify the slope and the y-intercept for both of these equations, we can graph them. The slope for this first equation is positive 2/3. And the y-intercept is positive 3. So I'll start by plotting the y-intercept, because that's the point at which the line intersects the y-axis. So there's a point here at positive 3. And then if the slope is 2/3, remember slope is change in y over change in x. And so if that's 2/3, I just need to go from the point I plotted, the y-intercept, or any point on the line, and I need to move according to this change in y, change in x. If change in y is positive 2, it means I'm going up 2. Change in x is positive 3, it means I'm going to the right 3. 1, 2, 3. And so my line will pass through these points. Like this. Okay, this other line, get a different color here. Same thing, actually the same slope, m is equal to 2/3 again. Subtracting 4 is the same as adding the opposite of 4 or adding a negative 4. So the y-intercept here is negative 4. So again, we'll start by plotting the y-intercept point, and then I'm going to follow this slope, up 2, right 3, up 2, right 3. I can even plot more than one point if I wanted to, up 2, right 3, up 2, right 3. So the line will pass through all of these points, like this. The question then asks, what do you notice about the graph lines? The graphed lines, they're parallel. How could you have determined this before graphing them? The fact that the slopes are equal, both slopes are 2/3, results in parallel lines. If the slopes are equal, the line should be parallel. Okay, moving on to problem 4. This is the first thing we did in this unit, combining like terms. And so, actually I'm not going to go in the order that it's given. I'm going to go in a different order and come back to the first one in just a second. But if you look at this expression, we have here in this term we're counting b. We have the opposite of 2 b's. In this term we're counting c. We have 7c. In this term we're counting b again. We have 15b. I can combine this term and this term because in both of them I'm counting the same thing. I have negative 2b and 15b. If I combine those, I have 13b. In this term I have 7c. Remember, terms are separated by addition and subtraction. In this term I have c squared. Now that's not the same as c. C is one-dimensional, c squared is two-dimensional. C would be like, if I had c squared, it would be like a square that had length c. That's c squared. But c is just this length, so I can't combine this length with these areas. It's not the same thing. We're not counting the same thing. And so c cannot be combined with c squared, but this term, positive 7c, can be combined with this term, which we could think of as adding a negative 9c, because subtracting is the same as adding the opposite. So 7c and negative 9c would be negative 2c. So I have 13b plus negative 2c minus 3c squared, or plus a negative 3c squared. And it's good to think of it as adding a negative 3c squared, because it's best to format, or it's good convention to write these with the highest order term first. So the c squared should go first. So I should start this as negative 3c squared plus 13b plus negative 2c, or minus 2c is equivalent also. So that's how we do the second one. Okay, going back to the first one, this is a little trickier because we're subtracting this quantity x minus 9. So this is like having a negative 1 outside of the parentheses. I need to distribute that negative 1 to both terms. If I multiply negative 1, I'm just taking the opposite of what's inside here. The opposite of x is negative x. So I have x squared plus 3x plus a negative x plus negative, the opposite of negative 9 is just 9, so plus 9, or negative 1 multiplied by negative 9, or subtracting a negative 9. Any way you want to think about it, this is positive 9. Okay, so here I have x squared is the only term that has x squared in it, so it's just going to be x squared. These two terms are like terms, the 3x and the negative x. Those like terms can be combined for 2x. And then finally I have the constant term 9. So x squared plus 2x plus 9 would be the simplified expression. This last expression, in this term I'm counting wholes. In this term I'm counting d cubed, which would now be three-dimensional. In this term I'm counting d, one-dimensional. In this term I'm counting d squared. So I don't have any like terms in any of these terms. So it can't be simplified. I will, however, rearrange it because it's best to write the highest order term first. So I'll realize that subtracting 2d cubed is the same as adding negative 2d cubed. So I'll start with negative 2d cubed, subtracting 5d squared. So I could write minus 5d squared or plus a negative 5d squared plus 7d. And then we'll end our expression with the constant term 12. Okay, that completes page 1. We'll continue the review video with page 2. Thank you.